Okay, so we're going to look at starting the idea of circuits and the difference between this chapter and the previous chapter. The previous chapter was electrostatics, and we were looking at if we had charges that were fixed in place, then at just an instant in time, what was the forces between them, what was the energy, and then sometimes that energy got converted to kinetic energy, and then we looked at this point in time what's kinetic energy. With circuits, we're looking at the movement of charges, the continual movement of charges. What causes charges to flow, what causes them to be impeded from movement, etc. So this is the unit of circuits. And the first thing we're going to look at is this idea of voltage difference or potential difference. And we've kind of looked at this already in the previous chapter, but in terms of how it relates to circuits, it's just this idea that if 2 points that have differing voltage are connected, so 2 points that have different voltage are connected, then electrons will flow from the point of high potential to the point of low potential. And this is kind of similar to gravitational potential difference. If you have a point up here that has a certain amount of gravitational potential and a point down here with a certain gravitational potential, and you provided a pathway for mass to travel through those 2 points, then the mass is going to travel from high potential to low potential. The one difference is that with mass matter can just flow through air. It's very easy. With charges, usually we need some kind of a conduit or a wire for the charges to actually move from one place to the other because the air just impedes its movement. So we are primarily going to be looking at the voltage difference. That's going to cause something. Technically, the symbol is a change in potential or a change in voltage, but because normally we'd say that one of our voltages, we'll call it V1, I'll say it V2, because normally V2 is at 0 volts. This then just becomes just voltage. So we're not necessarily going to write out delta V. It is a difference in voltage, but we don't necessarily care like what those absolute points are. We just care that there is a difference between them of a certain value. Okay, so like if V1 is 12 volts, our potential difference is just 12 volts. And so normally we'll just call it V is 12. That's the potential difference of our system. Okay, so that gets us into the idea of current. And we're going to define this starting off with what's called conventional current. And we looked at, I have to sneeze. So if I have 2 points that have a potential difference and I'm looking at connecting them, then conventional current is the amount of current that flows past a given point in a certain amount of time. And I talked about this earlier with the fact that technically it's the electrons that are moving, but remember when they first defined it, they didn't really know which ones moved, and so they just assigned it was the positive ones that moved. So conventional current is the direction that positive charges would flow. And we just kind of have to go with that definition. It's a wobbly board. And so we just need to know that electron flow is actually opposite conventional current. The symbol for current is a capital I. When we get back into class, I'll explain where the I comes from. And the equation is right on the definition. I is equal to the amount of charge that flows past a given point in a given amount of time. So I is equal to Q over T. And if we think about the units, charge is measured in coulombs, and T is measured in seconds. And so coulombs per second becomes a new unit called an ampere. And sometimes it's abbreviated as an amp, or sometimes we just abbreviate it as a capital A. So let's just go through one example of current. So this problem says, how long would it take for 0.003 coulombs of charge to flow past a given point in a wire that carries a current of 1 nanoamp? So in looking at the quantities that this problem gives us, 0.003 coulombs is Q, and we're looking for how long, so we're looking for what is the time. To pass a given point in a wire that carries a current of 1 nanoamp, so that is my I value. So this is pretty straightforward. I is just equal to Q over T. So I've got 1 nano. Nano is times 10 to the negative 9 is equal to my charge, so 0.003 over my time. And go ahead and try to calculate that out. If you want to pause the video, go ahead and pause the video. And when you calculate that out, the time, it's a really big amount of time. It's 3 million seconds. And that's just kind of give you an idea, because that's a pretty small current, 1 nanoamp. But 0.003 coulombs is a big amount of charge. That's a lot of charge that we're waiting to go by for such a small current. Okay. Now with current, there's actually 2 types of current that one can have in a system. They are direct current and alternating current, AC and DC. So let's start off with direct current. So this is going to be current that only flows in one direction. So with direct current, you have this net movement all in one direction. And current is actually just a collision between charges. So you've got these electrons and they're continually colliding. And they're going kind of from atom to atom to atom to atom. And the electrons are physically moving from one place to another. That's the idea of direct current. And the sources of direct current are batteries. So you've got some kind of chemical reaction that is causing the anode and the cathode to have a different potential. And when you connect them, then because of that difference in charge, you're going to have the electrons physically move from one to the other. And then the second one is alternating current. And so this is going to be current that is continually changing directions. It's almost kind of like the collision is like swaying back and forth. Well, I can't spell. And the reason this is alternating is because essentially there's an electric field that's causing the electrons to move, and that electric field is being turned on, off, on, off, on, off. So the electron moves, and then it's off, and so then it just drifts back, and then it moves, and then it's off, and it'll just drift back. It's like resting position, we'll say. And when we talk a little bit about drift velocity, that'll make a little bit more sense. So it's current that's continually changing directions. Its sources are generators. And this, in fact, we can kind of think of it more as like our outlets, because all of our outlets are driven by electricity being generated somewhere, whether it's a power plant nearby or a power plant further away. There's something that is generating electricity. It's not a stored electricity. And this swaying occurs at a certain rate. So here in America, that swaying occurs at 60 hertz. So you may have seen like in an outlet or some kind of a plug where it has kind of like the electronic specs on it, and it'll say 120 volts, 60 hertz. That hertz value is that swaying back and forth. If you go to different countries, sometimes it's a 50 hertz cycle, and the device may not work as well when it's at a different cycle. Now, why the differences? Direct current is nice because it's portable. You can make batteries that are really small, not have any wires plugged in. Alternating is nice because with alternating, you have this swaying back and forth, and you don't have as many collisions. Now, every time you have a collision with direct current, you're going to lose some energy in that collision. You're just going to lose more energy to friction because you've got this electron physically moving down the wire. Whereas with alternating current, you don't have that collision. You don't have that electron bumping into everything, so you don't lose as much energy. So the benefit of direct current is there's a lot less energy, or the benefit of alternating current is there's a lot less energy lost to friction. So in terms of transporting electricity, alternating current is the better method instead of having batteries that run wires on and on and on. Now, with this idea of movement, let's talk about something called drift velocity. So innately, electrons are just vibrating. They're moving around just innately within the atom. And if you look at this, electrons move at about the speed of 10 to the 6th meters per second. So electrons just randomly move about 10 to the 6th meters per second. And that's without an electric field. That's just them just kind of jostling in every direction. Now, when an electron is exposed to an electric field, the electric field is going to give them an additional velocity. Gives them a velocity in a particular direction. And this is called the drift velocity. And this drift velocity, it's not that you end up having one electron that, because there's electric field, just goes zooming across. I mean, you can have that in a particle accelerator, but if you have just a whole, like a wire, you have a whole bunch of atoms and a whole bunch of kind of loose electrons, and they're exposed to an electric field, that drift velocity only gives them like a little bit of an extra velocity in a particular direction. But it's that, and that extra velocity is only like another 10 to, it's tiny. It's only like 10 to the negative 4 meters per second. So they don't move a whole lot in that little space. They do move forward, but they don't move a whole lot forward. But the collision that ensues, so the collision between electrons and the atoms, this is what happens at the speed of light. So when you turn on the light switch, it's not that you've knocked one electron and that one electron is moving through all of the wires and then it's igniting these fluorescent tubes. When you turn the switch on, it's basically causing that collision to happen at the speed of light. Okay? That one little electron that you initially hit, it moved a teensy bit forward, but it didn't move all the way through your wires.